All right, here we go. Let's talk about continuity. Continuity seems like it's a pretty easy topic to talk about because we know a little bit about it. But the problem is what we know is kind of informal. These are some of the things that we think about when we think of continuity. We think of things like no jumps, skips, or gaps. Sometimes people will talk about a function going on forever for it to be continuous. One of the definitions that we learn in algebra classes, you've probably heard this, is that if you can draw the graph of the function without picking up your pencil, essentially if you can draw it all in one take, then the function is continuous. If you have to pick up your pencil to draw it, then it's not continuous. The problem is that this definition isn't really that good. It kind of falls apart when we start looking at things a bit more in depth. So we're going to shore this up a bit using some calculus. So let me just draw some pictures of the things that we would normally say aren't continuous. Maybe we'd look at something like, maybe we'll draw our set of axes here, and we've got a function that looks like this. Just a classic piecewise function. And we'd say this is not continuous because there's this weird little jump that we have going on. Or maybe we could say there's like a hole in a function right there, and that could give us a bit of a problem. Or we could do something kind of similar, and we could do something like this. I'll put the point down here. All three of these things are not continuous. We would pretty much all be able to look at this and say that it's not continuous, but the explanation of that discontinuity is going to be something that we're going to have to build up and make a little bit more rigorous. So here's what we've got. For a function to be continuous, we're going to say three things. First, the limit has to exist. Second, the function value has to exist. And third, the limit and the function value have to be the same thing. Let's talk about all this stuff, but I want to notice one thing right here. When we're talking about continuity, let me fix that a bit. When we're talking about continuity, we're talking about it at a single point. We're not talking about functions as a whole yet. We're classifying points specifically as continuous points or not continuous points. That gives us the opportunity to look at a specific limit here. What we're saying in this first case is that the left limit has to equal the right limit. This is our normal thing for a limit to actually exist. In this second one, when we say f of a exists, what we mean is there's actually a y value here. There has to be a point on the graph. And then for the limit and the function value to be the same thing, what we're essentially saying is that the point has to be kind of on the line. Let's go back to the three pictures that we drew earlier, just in the last slide, and we'll just kind of point out where the definition of continuity is going to fall apart. So in all of these, we're actually looking at just this point here. We'll call it A, and here A, and here A. Notice in this first one, the limit does not exist. That's supposed to be an O. There we go. The left side and the right side don't match up to each other here. And so it's not continuous at this point because the left and the right side aren't the same. The limit doesn't exist. Here, the limit exists, but f of a, the function value, does not exist. There's a blank spot here. There's no y value for this x value. A, we could say, is not in the domain of f. And here, the limit and the function value exist, but in this case, the limit and function value don't match. Our limit is somewhere up here, because our left and right side are both approaching this kind of y value, but our function value, the actual point, is way down here. So we need not only for the limit to exist and the function value to exist, we need for them to match up. We need that point to be on the line. So when we're describing continuity, we should be describing these three statements here. A couple of quick notes that we can talk about. We can extend this to more than just a single point. What we can say is we'll look at an interval from A up to B, some open interval here. And as long as all the x values in that interval satisfy this definition of continuity, the limit exists, the function value exists, and they're the same thing. If it's continuous at all the points on this interval, then we can just go ahead and say it's continuous on the whole interval. So we could draw a picture of a graph and make it look like this, and we can say it's not continuous here. Let's say this is at like 2, but it is continuous on negative infinity up to 2, and it's also continuous on 2 up to infinity. The only problem is at 2, and so it's continuous on the other intervals. So that's something we can talk about. We can also talk about one-sided continuity. Basically, if we go back to this definition and we switch the limit statements to just like, let's say, limits on the left. No, I'll say right. I'll put the little plus sign in here. And if we had that the right-sided limit exists, the function value exists, and the right-sided limit and the function value are the same thing, then we could say we've got some one-sided continuity. If we go back to this, we could notice that right here, this is continuous on the right, because the right point and function are on the same spot. Basically, we can say the right-sided limit and that function value are matching up. So closed endpoints, essentially, we can include as long as we put like a little caveat here and say that it's just continuous on one side of there. Another example of this is like our square root of x function. It looks something like this. We'll notice that this doesn't go on forever, but we'll say that it's continuous. Maybe I'll put this right here. Continuous on the right at x equals 0. Our square root of x function doesn't exist for negative x values, so of course the left side limit doesn't exist. But the right side limit and the function value still match up, so we can say this is continuous on one side. So again, we're just going back to this definition, and we can talk about what's going on here. This can be either right side or left side, but that'll give us our one-sided continuity. So that's pretty much everything we need to know about continuity to do everything that we're going to do. Although there are some properties. We're going to be able to kind of continue to put these things together. All of these properties are pretty easy to prove once we realize that continuity is based on limits. Notice that this last statement that we have here of our limit, I'm going to erase the one side stuff so it doesn't distract us. Our limit equaling the function value. This has been our definition of an easy limit. We've been saying that if you can just take this value and plug it in for x and that's what you get, that's an easy limit. So basically we're going to say anything that had an easy limit is continuous everywhere. That means constant functions, any power function or polynomial are all continuous at any x value, because these are all ones where we could just take the x value, plug them into our function, and get an actual answer out of it. If two functions are continuous at a point, then we can add, subtract, multiply things, and the answer that we get are still going to be continuous at that point. Meaning we can take one polynomial function and add it to another polynomial function, and it's going to be continuous everywhere. We can multiply polynomials, and it's going to be continuous everywhere, because in all these cases, we're just getting another polynomial function. Rational functions are continuous everywhere as long as you don't divide by 0. When you divide by 0, we get vertical asymptotes where our limit doesn't exist and the function value doesn't exist, so of course they can't be equal. Or we could get these like indeterminate forms, 0 over 0, but we'll notice that in those cases the function value still doesn't exist. The limit might, but the function value doesn't. So any rational function is not going to be continuous anywhere you divide by 0. And we have to be careful about like square roots and fourth roots and things like that. Any even root. If n is an even number, then we can't put negatives under those roots. Notice that if this was odd, like a cube root function, then that's continuous as long as the stuff underneath is continuous. So here we need, maybe I should put this in here, or we'll say if f of x is not continuous. Because we could take a look at something like the square root of 1 over x, and we'll notice that this is going to still have a problem at 0. Even though it's not negative under there, it's because the stuff under the root gets messed up when you put 0 in there, because it's a rational function where we're dividing by 0. So we basically just have to use our own kind of common sense to put these continuity properties together. We'll be able to build some complicated functions and see what's going on. That shouldn't be too much of an issue. What we want to do is use this idea of continuity. What we're really going to be doing is using the intermediate value theorem. We call it something different in this class. I think it's called like sign properties on an interval. We'll talk about it in a second. But really what it is the intermediate value theorem, which you may have seen before. We'll try and remind you what it looks like. This is our sign properties on an interval theorem. It looks confusing. It is a little confusing. My guess is that if we read through this, it's not going to click on what this means. So I'll draw a couple pictures and hopefully that'll clarify things. We're going to say if f is a continuous function on the interval a to b, which means that it's continuous at all the x values in that interval, and f of x is not equal to 0 for any of the x values in that interval, then either the y values, the function values, are all positive or they're all negative for every x value, meaning any x value on this interval is going to spit out the same sign. They're either all going to spit out positives or they're all going to spit out negatives. The easy way of describing this is by separating our page by drawing a line right down the middle. I'm going to go back. I think I've got a little tool that lets me draw straight lines. There we go. That's better. Let's draw a nice straight line right down the middle there. And I'm going to put a person on this side. And what we want to do is try and get this person from this side to the other side. There's really only one way of doing it. They got to cross the line. So we're going to say, what if they're not allowed to cross the line? How can we get them from one side to the other if they're not going to be able to cross this line in the middle? And we could do a couple of different things. We could say, well, what if we are able to go like up and around the line? We'll say, well, let's pretend this line just continues the whole way up through the top and up through the bottom. So they can't like walk around the line. Well, the only real way that we can do this is by taking our person and just essentially teleporting them over. There we go. I did it. But I've also broken another rule. I've not been really fair with the rules of how this person can move, because we know that if this was like a real person in a real room divided in half, they wouldn't be able to just kind of like teleport from one side to the other. That is basically our continuous requirement. The movement of our person has to be continuous. So I'm going to go ahead and get rid of our person now, and we're going to make this a point. And we're going to say, how can we get our point here if we have to draw the path of it from one side to the other? Well, if we're going to draw the path, we can make it move around a lot. But if it's going to cross through to the other side, it's either going to cross the line, or if we do this again, maybe I'll do it in blue this time, we could do something like this. We could stop and we could pick it up over here. And then we could say, oh, yay, we made it to the other side. Either we have to cross the line or we have to break the continuity of our drawing. All of this looks really kind of silly, but let's go ahead and put this on a function now instead. So let me draw a set of axes. I'll do them in my regular green. And now what we're going to say is that we're going to pick a point. Let's say this is A and this is B. And we have to be in between here because we're just looking at this interval. And if we pick a point to start here and we draw a graph and it's continuous and it doesn't ever equal 0, meaning it doesn't cross the x-axis, then the only thing that we can do is basically stay above here. Similarly, if we started underneath and we have to be continuous and we can't cross through, then we're just going to stay below, meaning we're either always going to be above the x-axis or we're always going to be below. We can't get from one side to the other unless we cross through somewhere in the middle or we break continuity. That's really what this theorem is saying. This is a really useful theorem for a lot of different things. We're going to start really slow and then we'll bring this back later. So what I want to do is just take a look at a definition of something that we'll basically use here, just so we use the same terminology. And then we're going to solve an inequality. We're going to call these things partition numbers. A partition number is an x value where either our function is not continuous here or it equals 0. Basically what we'll notice is that those are the spots where it breaks this theorem. It's either going to not be continuous or it's going to equal 0. There's places that we can cross from one side to the other. We'll call those things partition numbers. The way that we would normally solve this inequality is by trying to do some algebra, but it gets a little tricky here with inequalities and rational things. So what I'm going to do is first find the partition numbers. The partition numbers are pretty easy to find because we're just going to look at this function. We'll call this f of x. And we're going to say, that's this whole thing, not just the top. We're going to say, where is this equal to 0? Well, this is just a fraction of things. Fractions are always equal to 0 when the numerator is equal to 0. So what we're going to do is we're going to say that this is equal to 0 at x equals -1. So we can say f of -1 is equal to 0. So -1 is going to be one of our partition numbers. The other one is going to be right here at x equals 2 because f is not continuous at x equals 2. Because if we put 2 into there, we divide by 0. And we said that rational functions aren't continuous when you divide by 0. So we have 2 partition numbers. What we're going to do is we're going to set up a bunch of intervals here. So we're going to use these partition numbers to build what we'll call a sign chart. And that's what our textbook, I believe, calls them. We're going to do it this way. We're going to start with intervals of x values. We call these things partition numbers because we're going to take the real number line from -infinity up to infinity, and we're going to cut it up. We're going to partition it at these points. So we're going to look at the interval from -infinity up to -1. Then we'll look at -1 up to 2. Then we'll look at 2 up to infinity. If we had more partition numbers, we'd have more intervals, but we're essentially just going to use these to take out of the real number line. Now, the thing that you'll notice is that since these were our 2 problem numbers for that theorem, this means that our theorem is going to hold on these 3 intervals. Let's go back and see what this means. Since those 3 intervals that we found are continuous and not equal to 0, because we took the only kinds of points that could be not continuous or equal to 0 out, then we know that each of those intervals are either going to be always positive or always negative. Since we want to look for the ones that are negative, what we can do is just find the signs of these things. So let's go ahead and find the signs. The way that we can do it is by just picking a test value. So let's test x equals, I don't know, something between -infinity and -1. Let's just pick like -4. That's in that interval. And we're going to plug that into our function. And we're going to say f of -4 is equal to -4 plus 1 over -4 minus 2. That's going to be -3 over -6, which is half. All we care about is the sign here. Positive. Let's go ahead and do the same thing here. Let's test x equals 0. F of 0, if we put 0 into this thing, we're going to get -half. That's going to be negative. And finally, we'll go ahead and pick a test value from this interval. Pick any x value that's in between 2 and infinity. Let's just say 3. And we're going to look at f of 3. That's going to be 3 plus 1. That's 4 over 3 minus 2. That's 1. So that's going to be 4. That's a positive y value. Now, we're only finding one of the y values on this interval, but since this interval satisfies the theorem that we have, we know that all the y values on this interval have to at the very least be the same sign, because this function can't cross over from one side of the x-axis to the other, since we picked out the 2 spots where it was either equal to 0 or discontinuous. So now we can go back and we can say, all right, if we're looking at this inequality here, where is it less than 0? Well, this is the one. If we switch this around and we were looking at trying to solve x plus 1 over x minus 2 is greater than 0, then we look at our other 2 inequalities. And we can just answer, maybe I'll just put this here. Our answer is just -1 to 2. So we can just list whatever intervals are going to work for that. This process, again, is called creating a sign chart. So maybe I'll write that here. All this stuff is called a sign chart. The reason we call it that is because this kind of looks like a little chart that we've got. We're picking up intervals and working our way down with them, and we're looking at the signs of the function there. So we'll use this to solve some of these weird inequalities. But what we'll really do is use this for some analysis later on when we start trying to figure out what's going on with certain aspects of functions. We're going to care a lot about the signs of things later on in the semester. So we'll use these partition numbers, we'll call them. That's just these values that we're picking where we're going to split up our intervals and then build our sign chart from there. So give that a shot. And again, let me know if you have any issues or questions or anything like that.